Hello and welcome to another session of the Assumptions of Physics reading group. We're still waiting for a few people to join, and if you are looking at this video and want to join as well, you can send me an email at my Umish address and I'll set you up. So let's see if there is anybody else coming. I don't see anyone else joining. So it seems that we are only three people for now. I'll put the reading order in the chat, and I'll share the link on the chat. And I'll share the text. Share. There we are. Okay, so now we also have Alina. And there we go. So I think we were at the multiple degrees of freedom. We finished with the Hamiltonian 1 degree of freedom. We saw that there were 12 equivalent conditions. And I think we should just start. I think Rudra is the first one.
Yeah, uh, we've seen how dr is a constitutive assumption for Hamiltonian mechanics, and in fact is equivalent to Hamiltonian mechanics for 1 degree of freedom. We now turn our attention to the general case, and we will find that dr by itself is not enough to recover the equations. We will need an additional assumption, that of the independence of degrees of freedom.
Artem?
Yep. First, let's take Hamilton's equations for multiple degrees of freedom and re-express them in terms of generalized state variables. This will be denoted as xi a and will span a 2n-dimensional space, i.e. a manifold. The displacement field will be the time derivative of xi I, which again is the vector field that defines the evolution of the system in time. Hamilton's equation then can be expressed as, similarly to the previous case, okay, I kind of overstepped, but it's fine. Let's introduce the following matrix, which is our previous omega matrix, but its tensor product was the unit matrix, which performs a 90-degree rotation within each degree of freedom, switching the components between position and momentum. That is, if the VA is that, then by multiplying it with the omega matrix, we get a switch of degrees of freedom and a minus sign. And footnote 21, for those versed in simplectic geometry, VA times our omega AB are the components of the one form. However, we are not going to call it a one form, as that assumes that the whole object is a map from a vector field to a scalar field, and we do not know whether that is the correct physical understanding. In other words, we want simply to understand what the quantities are doing without being tied as much as possible to a particular way to frame it. Full reverse engineering of differential geometry will be done in a later chapter once the physics we need to describe is clear. And then we can rewrite the Hamilton's equations using that matrix, which notationally is the same as HMG, which was the same equation, but for 1 degree of freedom. Wait a bit, I need to scroll back. Where was I?
Back button.
Oh, does that work?
Yeah, I just did it right now.
It doesn't work for me. I'm gonna just read
Okay.
from Zoom.
Yeah.
So the insight that the displacement field is equal to the gradient of the Hamiltonian rotated 90 degrees still applies, except there are now multiple ways in principle to do that rotation. It is only the one defined by the omega AB matrix that works.
Okay, so
Okay.
let's unpack all of this. We have, as usual, our multiple our equations. This time in multiple degrees of freedom. We still have this matrix that does a rotation, and you can really see here that this is the, let's say, the action of the matrix within a degree of freedom that does the switching and putting the minus sign. And this is, let's say, what does the matrix do across degree of freedom, and it just leaves each degree of freedom by itself, right? So whenever we have our vectors that has component in position and momentum, the position and momentum components get switched inside each degree of freedom with a minus sign. And again, this now is equivalent to this, except that the switching at the minus sign is done on the S side instead of being done on the H side. So those are the same equations. Okay.
Okay. Conditions dr divergence Jacobian that's probably
Volume, yeah.
volume conservation. I'm losing
And density conservation.
and density conservation are still satisfied and equivalent to each other. In fact, the divergence of the displacement field is zero, as there, and the Jacobian is unitary. So the first order term is again the divergence. The Jacobian is still the multiplicative factor between past and future areas and then densities, and therefore they are conserved even in the case of multiple degrees of freedom.
Okay, so again, this is just calculation, and this is essentially what we had for the single degree of freedom. It's just that you have multiple indices, multiple Q's and multiple P's, but when we apply Hamilton's equation, it's still the same, and you still have the fact that you're just switching the derivative, and so this cancels out. The same thing when you go and calculate the Jacobian, you have the position that changes based on the displacement field. And so you have this sort of identity on the diagonal plus this variation. And again, this is a block matrix. So the total determinant is the determinant, the determinant of the blocks. And therefore, the leading term is still this 1 plus the divergence, and therefore, again, the fact that divergence is 0 means that the Jacobian is 1. So all the things that we saw for the single degrees of freedom for these conditions apply exactly in the same way. You just need to add indices. Alina?
Right. However, these conditions are not equivalent to HM and D. Displacement field as A has 2n components and is therefore specified by 2n functions. Conditions of divergence, Jacobian, bond conservation, density conservation specify the same single constraint, bringing down to 2n minus 1 the number of independent components. The choice of Hamiltonian provides another constraint, leaving 2n minus 2 choices undetermined. In the single degree of freedom case, n equals 1. No choices are left, and therefore the displacement field is fully constrained. In the general case, however, this is not enough to fully characterize the evolution. Therefore, HMD implies all of these conditions, divergence theory, Jacobian, unitary, bond conservation, density conservation, but the converse is not true.
Let's see what happens to condition DI simp. The invariance of omega in the general case. We have, therefore, the invariance of omega AB is equivalent to yada, yada, yada. In terms of the rotated displacement field SA, we have the more compact form. And this tells us that the rotated displacement field SA is curl-free, which
Okay,
is the same condition. Yeah, we can.
let's go through the
Yeah.
math, otherwise it's so again, this is just a conservation of omega. So this is omega after the motion. This is the omega before the motion with the Jacobians in both sides. And so this, as we saw before, is just the identity plus the variation given by the displacement fields on both sides. This is a Jacobian. And this is where the fun starts. So we collect the first order term, which is just the deltas applies, the Kronecker delta to applies to omega CD. So what you basically have is that you are changing CD into AB. So the transformed omega is to a first approximation the omega. I think there was a question on the chat that got retracted. Okay. Then we take now the first order term, like the first order term in dt. And so you have this applied to omega CD, and you have this applied to, again, omega CD. So here you're essentially contracting the C, and here you're contracting the D, right? And now because and then you have the second order term that we're not going to care. Now, because omega is made of constants, right? We saw it's 1, then the partial derivative omega is 0, so we can bring it inside the derivative. So the derivative of S contracted with omega is equal to the derivative of S contracted to omega. And so we bring both these inside the derivative, and then you can see that this is contracted with the first index, while this is contracted with the second index. And we want it to be the same, so we switch the order of here. This AD becomes the A, but since this omega is antisymmetric, we get a minus sign here. And now this is the leading term, and if we want this to be equal to this, then the first leading term has to be equal to 0. And so you see that this is essentially the curl of this term, right? So now this is the term that is curl free, and it's the thing that then is going to get a potential. So if we remember, we have this is essentially the one contractor is just the displacement field rotated 90 degrees, and so you just let the curl of that is equal to 0. And this is like, to me, the fact that it works so nicely in the math, that it's not that complicated if you know how to do the math in components. It's quite nice. And so, Robbie, did you already read this? I don't remember.
I don't think I finished it. I'll just say it. This tells us that the rotated displacement field SA is curl-free, which is the same as condition di curl, and therefore di curl and di symplectic are equivalent conditions also in the general case.
Okay. Rudra, back to you.
Note that the Hamilton's equations state that the rotated displacement field is the gradient of the Hamiltonian, and therefore we have the curl term being set to 0 in equation 1.61, which simply verifies that the curl of the gradient is 0. Conversely, if SA is curl free, then it admits a scalar potential H such that SA lower A through the index lowering equals partial with respect to A of H, which recovers Hamilton's equations. Therefore, HMND, DI curl, and DI simp are equivalent.
Okay, so this was the most straightforward way that I was able to find to show that essentially Hamiltonian mechanics is equivalent to the conservation of a symplectic form. You basically see it coming out of the equation, and again, it's a kind of vector calculus. It's just that it's a vector calculus in in essentially n dimension. The vector calculus that we study with div, curl, and gradient, they only work in 3 dimensions. So we are doing something that zero generalizes. Artem.
Yes, so the relationship between Poisson brackets and omega AB is the same in the general case. Therefore, di POI, which one was that?
It's Poisson.
Poisson and di symplectic are equivalent as well. Okay, that was short. To sum up, in the general case, HM and D, HMG, di simp, di Poisson and di curl are all equivalent and therefore full characterizations of Hamiltonian mechanics in the general case. These imply dr div, dr Jacobian, volume conservation, and density conservation, which are all equivalent to one another, but weaker conditions that cannot recover Hamiltonian mechanics in full. For the second set of conditions, we already have an intuitive geometrical picture. The net flow of the displacement within a region of phase space is zero, volumes are preserved, and so are densities. We need to build a stronger geometrical intuition for the first set, which is actually the more fundamental one.
Ruli?
Okay, I'm sorry. Condition di symplectic tells us that VA omega AB WB is a conserved quantity no matter what vectors VA and WB we choose. In the case of a single degree of freedom, this represented the area of the parallelogram formed by the two vectors, which is also the volume of the region. In the general case, we still have two vectors, but the situation is a bit more complicated. We can gain an understanding by looking at the outer product decomposition for omega AB we saw in SFND. This tells us that what happens within a degree of freedom is different from what happens across degrees of freedom. If you pick a single degree of freedom, x between 1 and n, and two vectors v is equal to well, something in terms of the conjugate momentum and or some multiple of the conjugate. Wait.
Right. So these are the components, and with E, I usually identify the vector, the basis. So V is just the component in Q and P, and these are the component in of W.
So some conjugate momentum degree of freedom stuff and some position degree of freedom stuff, right?
Yeah.
And W that stretch along the degree of freedom, then we have VA omega AB WB is equal to just V QWP minus VPWQ. Yeah, just by expanding really. That is within each degree of freedom, omega AB computes the area of the parallelogram. Since omega AB is conserved parallelograms within any degree of freedom, where we map to parallelograms of the same size.
Alina.
If we pick two different degrees of freedom, x and y, and two corresponding vectors v and w, then we have VA omega AV WB equals 0. This defines the notion of orthogonality between different degrees of freedom. Since omega AB is conserved, this notion of orthogonality is preserved during the evolution. Orthogonal degrees of freedom are mapped to orthogonal degrees of freedom. Those familiar with general relativity and/or Riemann geometry may gain more insight by the following analogy. In those cases, the metric tensor Gij defines the geometry by defining the scalar product between vectors. That is, by given two vectors Vi and Wj. Vi, Gij, Wj is this inner product. Therefore, the metric tensor defines the length and angles for vectors. In Cartesian coordinates, the metric tensor is a unitary matrix of the same dimension of the space. The form omega AB does something in some sense similar and in some sense different, and defines areas within degrees of freedom and angles between them. Hamiltonian evolution preserves these areas and angles.
If areas and orthogonality are preserved, then volumes are preserved as well. The volume of a parapolipid formed by parallelograms on orthogonal degrees of freedom will simply be the product of the areas of the parallelograms. Therefore, we can understand why Hamiltonian mechanics satisfies dr volume. We can also understand why dr volume is not enough to recover Hamiltonian mechanics. An evolution could stretch one degree of freedom while shrinking another by the same amount. The total volume would remain the same, even though the area in each degree of freedom would not. For example, take the system of equations.
Okay, so you have the 2 degrees of freedom 1 and 2, and you can kind of see that on 1 degree of freedom, you have a damped harmonic oscillator, you have friction, right? You have a particle with linear drag, and because the momentum is going down. On the other degree of freedom instead, the momentum is increasing, so it's sort of driven. On one degree of freedom, you're damped, and the other one you're driven. Okay, so this is what these equations are doing.
The first degree of freedom is a particle under linear drag, while the second is a particle accelerated, not decelerated, proportionally to its momentum by the same coefficient. We can verify that the divergence is 0. And
yes, exactly. So the divergence, you just take all these elements and you take the derivative with respect to the same variable. This one gets a b, this one gets a minus b, and this gets a 0 contribution because these are not functional. This is not a function of q1, this is not a function of q2, and so the divergence is 0.
Therefore, dr divergence and dr volume are satisfied. However, the curl is not 0.
Right, so we can double check. This is, we just do the one between Q and P for the first degree of freedom. So you have SQ1, which is P1 over M, and SP1, which is minus B P. So again, you get a B from this side, but you get nothing from this side, and so the curl is not 0.
So di curl is not satisfied, nor are di symplectic and HMND. What was HMND? Yeah.
Hamiltonian mechanics with n degree of freedom.
Okay. The system is not Hamiltonian precisely because we are not preserving the areas within each independent degree of freedom. The first is shrunk and the second is stretched.
This is where if I kept doing pictures, I ran out of steam. If people want to contribute pictures and help me like put these things, but then you can basically imagine, you have the two orthogonal areas in 1 degree of freedom, the other degree of freedom. One is shrinking, the other one it's expanding, but the product remains the same, and so the volume remains the same, right? That's essentially the geometrical aspect of it.
So basically, would it be true to say that those conditions that do not imply Hamiltonian mechanics in n degrees of freedom, we just need to apply them to each degree of freedom, and then it works, right?
Yeah.
Okay, so yeah, go on.
The thing that's complicated is that all this idea of like this parallelepiped, it's all local. So in principle, Hamiltonian mechanics can still curve things, like the degree of freedom that started before, let's say, as flat, it starts becoming all twisty, and in fact, it can even become very complicated because, as we said the other time, Hamiltonian mechanics still are like chaos, right? So the degree of freedom, as it evolves, it can become very twisty. But then locally, you can always talk about parallelepiped in areas, and those conditions always have to remain the same.
Now that we have a more precise understanding of the mathematics and the geometry, we should turn to the physics. Note that the previous physical conditions, dr, EV, okay, let's remember what that was.
Deterministic and reversible evolution.
Okay.
EV for evolution.
And the next one was
Thermodynamics.
thermodynamic reversibility, right? And this one is preservation of information. And this one was
uncertainty of peak distribution.
Okay. And those are equivalent to volume preservation and that the Jacobian is unitary. Therefore, determinism and reversibility is clearly a constitutive assumption of Hamiltonian mechanics in the general case, but it cannot be the only one. Ideally, we would like to find a condition that is independent of dr. However, we saw that symplectic implies volume preservation. Therefore, the mathematics does not already give us two independent conditions we can map to the physics.
So this is an important point for me because the fact that we have math and physics and we would like to understand the physical conditions and the mathematical conditions, sometimes things do not map one-to-one. So the same mathematical condition actually is two separate independent physical conditions that are bundled together. And it could also be the same thing in reverse, so that you have in principle one physical condition, but then it needs to be specified in two, in principle, mathematically separate mathematical conditions, and then you can only see that those conditions are related when you go to the physics, because mathematically they seem to be two arbitrary separate conditions that you can have one without having the other. So when you're doing reverse physics and you're trying to go map, to map things back and forth, you have to be aware of this because things may get a little bit complicated.
This is an important aspect to understand for reverse physics.
That's exactly what I said. Sorry, go ahead.
The mapping between physical and mathematical conditions need not necessarily be one-to-one. A single mathematical condition can map multiple physical ones, or the same physical condition can map to multiple mathematical ones. We saw before the determinism and reversibility forces the evolution map to be both bijective and volume preserving. Mathematically, these are two independent conditions. We can have a bijection that is not volume preserving, for instance, a linear transformation that stretches one side, or a volume preserving map that is not bijective, for instance, a map from R to R that maps all rationals to zero while leaving all irrationals the same. Yet a physically meaningful deterministic and reversible map must do both. Here we have the opposite. Hamiltonian mechanics implies determinism and reversibility, but is also implying at least another physical condition. We need to understand which and whether it is physically independent.
Okay, I think my connection is kind of unstable, so let me know if it gets messed up. Let's start from what we have already established. The phase space volume quantifies the number of states in the region. This stands to reason that the area on each degree of freedom identifies the number of configurations for that degree of freedom. Therefore, given two vectors v and w constrained on a single degree of freedom x, the area of the parallelogram that identify VQWP minus VPWQ quantifies the number of configurations. Therefore, omega AB returns the number of configurations within each degree of freedom. What about between degrees of freedom?
As we saw, the conserved volume represents the total number of states, and it is the product of those degrees of freedom that are orthogonal. In terms of WAB, x and y are orthogonal if WQX QY equals WQX PY equals omega PX QY equals omega PX PY equals 0. In this case, the volume is simply the product of the phase space areas on the x and y degrees of freedom. This means that the total number of states is the product of the configurations of each degree of freedom. Physically, it means that a configuration choice for X does not constrain the configurations for Y. This means that the degrees of freedom are independent.
Given that there are different notions of independence, let us go through an example. Suppose we have a rabbit farm and describe its state with the number of males and females. These two variables are independent. If we say there are 231 females, it doesn't in principle tell us anything about the number of males. Now we may expect the population of both sexes to be about equal, and we may even find that in most rabbit farms that is the case, but this does not describe something about the nature of the variables themselves. It describes the nature of rabbit farms. Chicken farms, for example, would be predominantly females, as those are the ones that lay eggs.
Now we could choose to describe the rabbit farm with another set of variables, the number of females and the total number of rabbits. In this case, the variables are not independent. You find that there are 231 females. It tells us in principle that there must be at least 231 rabbits. Conversely, if we find that there are 231 rabbits, there can only be up to 231 females. This dependence is not a feature of the rabbit farms. It does not just happen to be that there are no farms where the number of female rabbits exceeds the total number of rabbits. There can't be one.
This type of independence is very different from the notion of independence in terms of statistics and probability. The latter is in terms of whether the probability distribution factorizes. That is, if P of F and M is the probability that a particular rabbit farm has F females and M males, the distribution of males P of M and females P of F are independent if P of F and M equals the product of P of F and P of M.
We therefore have two notions of independence. One is on the variables themselves and whether they can allow, i.e., whether we can measure different combinations. One is on the probability distribution we may have in a particular case and whether it factorizes. The orthogonal directions in phase space then are independent in the first, stronger sense. The degrees of freedom themselves are independent regardless of what probability distribution one may put on top.
One may ask whether there is a link between the two, and in fact there is. Going back to our rabbits, we can easily see that given any distribution P of F on the females, we can choose any distribution P of M on the males and set P of F and M to be the product of those. However, this does not happen for the total number. Suppose we chose P of F and we wanted to find P of F plus M such that P of F and P of F and F plus M factorizes into those two. The probability of the total number of rabbits could not change based on the number of females. If the probability of having 231 females is non-zero, then the probability of having less than 231 total rabbits in that case must be zero. But since we want the probability of having less than 231 rabbits independent of the number of females, then it must be zero for all cases. That is, the probability P of F plus M must be zero for all numbers smaller than the greatest value of F, such that P of F doesn't equal zero. If there is no such greatest value of F, for example, F follows a geometric distribution, no P of F plus M can exist that is independent of P of F.
The conclusion is that only independent variables can support independent distributions. Footnote 22. Formally, let omega f p be probability space. Let x a map from omega X and Y from omega to E. V be two random variables, and C and Z map from EX EV be the joint random variable, that is Z of omega is equal to X of omega. Then X and Y are independent in this stronger sense. If on the other hand you have this and are statistically independent of the cumulative distribution function of zxy is equal to f of x and of y, so that it factorizes. Alternatively, they are independent if the sigma algebra generated by the joint distribution z is the product of the sigma algebras generated by x and y, and are statistically independent of if the sigma algebra generated by x and y are independent in the standard probability sense.
So of course, if you haven't studied probability theory with the measure theory, this will make absolutely no sense because it's all just gibberish. But if you haven't, a probability space is defined by what it's called a sample space, which is all the things that can happen. And then you have a set of events, which are, it's an algebra of sets. And so, for example, if you have a die, a six-face die, 1, 2, 3, 4, 5, 6 would be the sample space, and an event could be the outcome of the die was even, right? Which is a set 2, 4, 6. And then what we're basically saying is that the fact that probability distribution factorize means that you have the product, but the fact that the variables themselves are independent, that then the space, the sample space, and the event themselves become a product space, and then on top of that you can put the probability distribution. So this is just making a little bit more formally precise what that intuition that we built with the rabbit farms means.
It should be clear that this observation is something that goes beyond the physical underpinning of Hamiltonian mechanics. It is something that applies to any variable to which we want to assign a probability distribution. As such, we do not want to expand the scope too much at this point, though clearly we will need to explore this more in full. Here we limit ourselves to the conclusion, concluding that the following four conditions are equivalent, and the conditions are: the system is decomposable into the independent degrees of freedom, the system allows statistically independent distributions over each degree of freedom, the system allows informationally independent distributions over each degree of freedom, and the system allows peak distributions where the uncertainty is the product of the uncertainty on each degree of freedom.
Did I take it from here? So the first means that the count of states factorizes. The second, that probability distributions can factorize. The third, that the information entropy can sum. And the fourth, that the determinant of the covariance matrix can factorize. Since only independent variables can support statistically independent distributions, I and D degrees of freedom is equivalent to independence of stat. Statistical independence of random variables coincides with independence of information entropy. Therefore, independence stat is equivalent to independence information. The uncertainty for peak distributions factorizes if and only if the joint distribution is the product of independent distributions. Therefore, independence stat is equivalent to independence uncertainty.
Clearly, these conditions are independent from dr. We can imagine a deterministic and reversible system that cannot be broken into separate independent degrees of freedom. And we can imagine a system that can be broken into separate independent degrees of freedom that does not evolve deterministically or reversibly. The question is whether assuming independent degrees of freedom and deterministic and reversible evolution is enough to recover Hamiltonian mechanics.
The first thing is to check then is whether we have enough constraints to recover omega AB, assuming that the system can be broken into independent degrees of freedom. we must be able to define the count of configurations for each degree of freedom, and independent degrees of freedom must be orthogonal. The fact that omega AB will return 0 if it acts on directions belonging to independent degrees of freedom is really telling us that omega AB counts not just configurations, but independent configurations. This, in retrospect, makes sense. But so far, this seems to restrict omega AB to be the tensor product of the our basically 1 degree of freedom symplectic form and a diagonal matrix.
Right. So you're basically taking the volume of each degree of freedom, but each degree of freedom might have a volume that is different from the other.
The fact that omega AB must return the area in each degree of freedom constrains the left matrix of the outer product to the one above. The fact that omega AB needs to return 0 across independent degrees of freedom constrains the right matrix of the outer product to be diagonal. However, there is nothing at this point that seems to constrain the area of each degree of freedom to map to the same count of configurations. Naturally, we could simply rescale conjugate momentum in each degree of freedom to homogenize the count, but this would be an arbitrary freedom. Is there something forcing all the AI to be the same?
Note that Qi and Pi are not the only variables that form independent degrees of freedom. If we take two independent degrees of freedom, x and y, x plus y and x minus y will also form independent degrees of freedom. That is, omega AB defines orthogonality for all degrees of freedom, not just those of particular bases. Changing x and y to x plus y and x minus y will effectively apply a rotation on the diagonal matrix to remain diagonal only if the coefficients of the diagonal are the same. This tells us that if we want omega AB to properly capture the independence of linear combinations of independent degrees of freedom, the diagonal matrix must have the same coefficients. This coefficient represents the freedom we have in choosing the units of omega with respect to the units of everything else. In the International System of Units, by convention, the product between Qi and Pi is in joules seconds, i.e. the same units of h, an angular momentum. And we set the coefficient to 1. Therefore, expressing the number of configurations with the same units for all degrees of freedom is not an extra constraint. It is necessary to keep track of dependency relationship for all degrees of freedom. Therefore, the other constitutive assumption of Hamiltonian mechanics is assumption I and D, independent degrees of freedom. The system is decomposable into independent degrees of freedom. That is, the variables that describe the state can be divided into groups and have independent definition, units, and count of states.
This assumption leads to conditions, degrees of freedom, statistics, information uncertainty, which we saw implies the existence of a form omega AB that defines the independence of degrees of freedom together with the count of independent configurations for each degree of freedom. Conversely, assuming HM and D means defining an omega AB such that I and D is satisfied. The last question is whether DR and so deterministic and reversible and independent degrees of freedom are enough to recover. Sorry, what is this? One more time.
Hamiltonian mechanics for n degrees of freedom.
Okay. As we saw, independence by itself means the existence of the counting form omega AB. Meanwhile, deterministic and reversible by itself means the conservation of the total number of states, the vault. Wait, is this an incomplete sentence right here?
Okay, as we saw, in the by itself means the existence of a mechanic form. Meanwhile, dr by itself means the conservation of total number of states.
No, this is good. Sorry. These two mathematical conditions by themselves do not lead to Hamiltonian mechanics. We need that the counting form itself is conserved, meaning that the DOF independence and the configuration count is preserved. This boils down to the following question. Does it make sense on physical grounds to have a deterministic and reversible evolution that takes a system decomposable into independent degrees of freedom and turns it into a system that is no longer decomposable? More specifically, can deterministic and reversible evolution take two independent degrees of freedom and break their independence?
We should remind ourselves that independence here is not statistical independence. Clearly, Hamiltonian evolution can add correlations and therefore evolve the product of two independent distributions into something that is no longer factorizable. This is not the question at hand. The notion of independence on the table is the one that tells us that all the combinations of configurations are at least possible. Recall the example of the rabbits. Number of females and total rabbits are not independent because we cannot have more females than rabbits. This is the type of independence we're interested in. Can deterministic and reversible evolution lose this type of independence?
The answer is, as you may expect, no. This is easily seen in the finite case. Suppose we have two integer variables, x between 1 and 3 and y between 1 and 3. If they are independent, we have a total of 9 distinct cases. If the evolution is deterministic and reversible, we will still have 9 distinct cases, which means the variables must remain independent. Note that we may introduce a correlation between x and y, but still we need 9 total cases.
The issue here is that the case of independent variables is maximal as it posits that all combinations of configurations are possible. Therefore, the only way to make variables no longer independent is to decrease the number of distinct cases, which cannot happen during deterministic and reversible evolution. The same must happen in the infinite or the continuous case, because finite ranges must still be comparable with finite sizes, which must hold the same property. Because finite ranges must still be comparable with finite sizes.
Say it again?
Is this finite ranges comparable with finite sizes? Why does that lead to the same happening in the infinite or continuous case?
So if you imagine that you have an infinite case of discrete elements, right? You need that whenever you have a region, is going to be mapped to another region. And so if you have deterministic and reversible evolution, the region that contains finitely many elements will be mapped to another region with finitely many elements. So
Okay.
now if you had a region that was factorized and you map it, again, you might have introduced correlations, but still you need to have a factorization of the number of cases on both variables. So since you can do it for all the sort of the finite sized sets, you have to do it for the whole space.
Okay.
And then for a continuum, it kind of works like that, but instead of going, outwards, you go inward. So again, if you have a finite size volume, well, the finite size volume is going to be the product of finite size areas. And so you move those, I still need the total volume to be the same, and I can't decrease the areas because the volume has to be still at least the product. It can't be more than the product. So it's a sort of the same thing.
Okay. Right. So these must hold the same property. Therefore, when we take both physical assumptions, independence on degrees of freedom, and determinism and reversibility, the physics tells us that independence of degrees of freedom must be preserved, which means preserving omega AB as well. In other words, in slide 1.69, Hamiltonian mechanics is exactly the deterministic and reversible evolution of a system decomposable into a finite collection of independent degrees of freedom.
This conclusion is yet another example of why just looking at the math is not enough. Two physical conditions taken separately may each impose one mathematical condition, but it is not necessarily true that imposing them together will only impose the conjunction of the two mathematical conditions. More than a problem with math in general, we believe it is an indication that the math we currently use is not the physically correct one, as it does not seem to be capturing the entirety of the physical conditions.
Note that in principle, we could ask the evolution to determine the independence of DOFs without requiring DR. As we saw, fixing all independent degrees of freedom fixes omega AB up to a scale factor, which could change during the evolution. The volume would stretch or shrink depending on the factor, stretching or shrinking each DOF by the same amount. An example of this would be a particle under linear drag in 3 dimensions. Since a faster moving object will be submerged to a greater frictional force, a spread in momentum delta P will become smaller in time and will tend to 0 as time increases. Given that the friction coefficient is the same for all directions, all degrees of freedom will shrink at the same rate. If we understand the volume as entropy, this tells us that the only way we can add or remove entropy to or from a system while preserving the independence of the degrees of freedom is by dividing that entropy contribution equally among each DOF. In other words, preservation of DOF independence gives us a sort of equipartition of entropy change. It is again striking to find these connections between disciplines at such a basic level.
To conclude, we now have a mathematically and physically precise way to characterize Hamiltonian evolution. We had found that Hamiltonian mechanics did not apply to all cases, and now we know exactly to which cases it applies. Systems described by finitely many independent degrees of freedom undergoing deterministic and reversible evolution.
And this is a perfect way to stop and see if there are questions. Oh, there is a question from the chat. If you have a system with multiple degrees of freedom, which is Hamiltonian, but degrees of freedom are coupled, that it still makes sense to assign or count of states separately? Yes. So the fact, this is exactly what we saw. The fact that you have coupling between the degree of freedom, it doesn't mean that they are not independent in the first sense. Like you still have all the possible product of states. It means that you're introducing correlation within the motion, so that if you have something that starts as statistical independent between the joint is a product of two statistical independent things, then they will become not statistical independent anymore. If you think it geometrically, so if you imagine that you start with two independent degrees of freedom, you basically can imagine that you have these nice surfaces of one, nice surfaces of the other that are always orthogonal to each other. And if you're evolving and you have correlations, you're going to see that these surfaces bend and bend in a way such that they are locally always orthogonal to each other, because that's what it is. But globally now they're not orthogonal anymore. So they're curved in one way, they're curved in one way, and the way that things are going to curve, it's exactly the type of correlation that they're gonna put. If you imagine instead that the degrees of freedom, for example, they all move, right? But they move in a way that the whole plane still remains orthogonal to the whole plane. That's exactly when you're not introducing correlation, because now you have something that was the product of this and this, and you move it around and it still remains the product. So the cool thing about doing reverse physics in this way is that whenever you have some intuition on one side, you can move it on the other. So if you want to have the intuition on statistical independence, you can now move it and say, okay, now preservation of statistical independence means preservation of this global perpendicularity, and not preservation of statistical independence means that the surface is going to bend and not become and not keep being straight. And I find that it's very useful to gain intuition and go from one thing to the other. Thank you for the question.
My question would be maybe
Wait,
that.
Artem, because there is a follow-up. In the same case, should we expect the degrees of freedom for different degrees of freedom are of the same size, meaning that all degrees of freedom are apples and not just the sum of apples and oranges? So this is where statistical, like the degrees of freedom are gonna mix, but you're still gonna map areas of the same size to areas of the same size. So you are still going to be able to not only compare the volume, but also compare the number of configuration for each degree of freedom. And that's exactly what the symplectic form allows you to do. It allows you to keep comparing these configuration on each degree of freedom. Artem?
Yeah, so my question is a bit unrelated, but here we define determinism and reversibility as this kind of stronger condition, not only like you map points to points and then you can go back, but also you map, you preserve like volume and phase space, right? So the question would be, the question is about quantum mechanics. Like there we, I mean, if we exclude measurement, we have basically deterministic and reversible evolution. But is there, but it's not, or maybe it is, but on the surface, it's not clear that it's the same strong deterministic and reversible evolution. It like takes a state to another state, and knowing the evolution, you can go back. But for me, there's not immediately this notion of maybe a volume, maybe an infinitesimal volume of like physically closed states that has to stay the same. Will we see something close to that for quantum mechanics, or does that like completely go out of the window?
No, yeah, the idea is that you can make all these parallels. So this is the part that I've been working for the past year and a half, and now I'm starting to do the reverse physics in quantum mechanics because I know how to make all these parallel. So you know that there is so Hamiltonian evolution in quantum mechanics, the Schrödinger equation, preserves information entropy. And you can show that, again, preservation of, given the state space of quantum mechanics, preservation of the von Neumann entropy is exactly unitary evolution. So you again get the same thing. What you don't have, and you're right, in quantum mechanics, you don't have areas in phase space, right? So that part of the geometric picture goes out of the window. But what you can do is, in the same way that you have the relationship between in thermodynamics, that the volumes are the logarithm, so the entropy is the logarithm of the volumes. You can define in quantum mechanics that the volumes are the exponential of the entropy. And there is some guy, Michael Holm, that actually wrote a paper like 20 years ago. It's one of those things that, I basically rediscovered, and I don't understand why this thing is not more widespread. But anyway, the cool thing is that he also showed that the uncertainty principle can be given a stronger form using these entropic volumes. And which means that the really it's tell you that the uncertainty principle is an entropic condition and not just about variances and so on. So the point is that if again you require the preservation of these entropic volumes, or the exponential of the entropy, of course it's going to be equivalent as conserving the entropy, and therefore you basically have a condition that maps to the other thing, right? It maps to the areas in phase space. In fact, the exponential of the entropy, like the work that we're doing on these generalized ensemble spaces, is to start for the entropy in a generic physical theory that might be classical or quantum, and then you define this volume by taking the exponential, and of course in classical mechanics they become the Liouville volume, the symplectic form, and so on, and in quantum mechanics that we have this thing. In fact, the cool thing about the exponential of the entropy in quantum mechanics is that for if you take a uniform distribution, let's say on a subspace, actually that volume is the dimension of the subspace. So if you take your block ball and you take the maximally mixed state, you take the exponential of the entropy, you are going to get 2 because you have, it's a maximally mixed state, a uniform distribution over a two-dimensional subspace. So there are all these parallels that sort of work a lot better than you would expect. The problem with quantum mechanics is that I don't know why the majority of people are always stressing the differences instead of finding the places where they are common. And if you start looking for the places, the things that they have in common, actually there is a lot of structure that is exactly the same. And so the point, as I said, I'm starting working on reverse physics for quantum mechanics. In fact, if you go to the here blueprints of the work ahead, you can start seeing that I have some parts on quantum mechanics there. It's sort of the first draft of the things that I'm writing. The goal is essentially to show that all these assumptions that we have here are also there in quantum mechanics, and that there is only one assumption that is different, that in classical mechanics, essentially you can take a system and think that it's made of small parts, infinitesimal parts, and these infinitesimal parts are, you can know everything about these infinitesimal parts. Instead, in quantum mechanics, you're going to have a sort of a lower bound that says, okay, you can know up to this level of description, and then anything below is not accessible to you. But then everything that you were saying on sort of the mixed state above remains the same for both classical mechanics and quantum mechanics. So I would have to go through a lot of details to show you all this, and part of the details I am still putting together, but it's gonna work. So all these things are gonna be 90% are gonna be the same. It's just the math that changes.
The follow-up question would be that I haven't myself studied this, but I know that you can do quantum mechanics in phase space.
Yes.
And so are there like good parallels there was what we have here for classical
That's what I'm going to do
mechanics?
my PhD on, actually.
There you go. So he knows more than me.
That's fun.
So I generally do not know if some of the things or what of these things can be generalized there. So there is this sense that there is the structure given by the Moyal bracket, which is a corresponding analog of the Poisson bracket. But actually, I have never even thought to say, is there a symplectic form type structure on quantum mechanics in phase space, and can that be sort of related in this? I quite frankly don't know. I don't know if you have any insights, but I actually do not know.
I think there's the problem is you have this homomorphism between the Poisson brackets and the Lie brackets or the commutators, but then it's not exactly mapping the classical physics to the quantum one, because it's lots got to do with the representation. So
Yeah.
the part of the challenge is constructing something like a Poisson bracket, which will actually map it precisely. There's many ways you could think of, maybe generalized geometry where you have the Courant bracket, or some deformation quantization where you consider power series of these Poisson brackets. It comes down to some arbitrary choice in some reduced Hilbert space. It's not precise right now.
So what I know, because we did it as in the paper where we show that the classical mechanics is a high entropy limit of quantum mechanics, we show that basically that limit that goes from the Moyal bracket to the Poisson bracket that typically is done by taking HR that goes to zero, it's essentially instead taken as basically doing a big stretch. So you do a big stretch and then things sort of become classical. But the fact though that you have to do the stretching not in the QP space that typically you do with the Wigner function, you just have to do it on the Yosemite Q, and then you can go back. So there are all isomorphisms there. So there might be a sense where you can use that to figure out what would be a sort of the equivalent of the symplectic form. But again, I have no idea. So these would be like very interesting question if somebody else were working on them and told me, and then we can integrate it with all these things. But yeah, basically, it'd be interesting to see that as well. Alina, you had a question?
Yeah, so Artem said in the Discord that it might be good for him if we can move the next session 1 hour.
Oh, right.
Is that good with everyone?
Yeah,
Up to you
thank you,
guys.
Alina.
It's good with me.
So I'd like to keep in general the same, like if it's a one-time thing, okay. If it's a better for you to have 11 anyway, then I'd rather just that we make the change once, because if we do it too often, I'm gonna tell you guys, I'm gonna forget at some point. Also
So
because
for me, it's probably gonna be a monthly call at my company. So this will be like once every 4 weeks or so. But the thing is, I don't know if it'll last. Like it should be at this time, but like if something like with the executives of the company changes, that will change.
yeah.
So if everyone is fine to move it to 1 hour later, like all the time, right now I'm expecting that this call at my job will be monthly. So yeah.
So executive decision, we just change up to 11. If people are on the chat on YouTube that they prefer to keep it at this time, please let me know. Otherwise, we are gonna do next week at 11.
Just
And
next week
then,
or from next week on?
yeah, from next week on, yeah.
Okay.
Because again, it makes, as I said, it's also, okay, so Julius confirms. It's better to me so that also when I'm planning other meetings and so on, I know that this is stable, and it's much better for me. So let's just move it to 11 and we keep it 11. Good. So are there any other questions on the physics? So there was a comment from Junius. There should probably be Ernest theorem for these notions. Yeah. Also, that's something that in principle I haven't seen. If sort of, let's say, on that there is another corresponding sort of classical quantum essentially on these things based on statistical averages. That's also something that I don't know. So since in quantum mechanics you can't define points of position and momentum, you can still define Gaussians in position and momentum, and so those Gaussians are what basically become, in the classical case, in classical limits to the points. So you're taking Gaussian that are smaller and smaller, and they become more and more orthogonal. And so in the limit, you have a basis with the Gaussian, because they're in the limit of orthogonal to each other. So I don't know whether there are also things like that that can be sort of done to recover some of these geometric notions of sizes of phase space. You go and look and study how the Gaussians, and maybe this is exactly what quantum mechanics in phase space does, because there's going to be some isomorphic between these things. But again, I do not know. Okay, anything else? Any other question? Because it's been already 1 hour and 10 minutes, so we are ready to stop. Done. So we're done for today. Thank you for following. Thank you for coming, and see you next week at 11. Bye.
Yeah, see you next week. Bye.
Bye.
Okay.